That's the question number 1 of paper 2, 2023, A-level chemistry. This question about rates of reaction shows figure shows an apparatus used to measure the rate of reaction when the acid reacts with an excess solid sodium hydrogen carbonate. When different monoprotic acids, organic acids are used, the rates of which gas escapes can be used to compare strengths of the acids. The time is started when the sodium hydrogen carbonate is added to the acid, and the mass of CO2 or gas loss is recorded at regular intervals. It's assumed that any change of mass is due to loss of CO2. So you got this picture here. So just the reason why using a conical flask instead of beaker would give you more accurate results in this experiment, because it reduces loss of liquid droplets. Okay? Right, we're doing this question now 1.1. It's 1.2. It says figure 2 shows that the results of this experiment with 25 centimeters cube of 2.23 mole cube solution of ethanoic acid reacts with excess of sodium hydrogen carbonate. Okay, so use figure 2 to calculate the rate of reaction 2 minutes. Reduce units of your calculated rate. So I did. I went to 2 minutes. I took the gradient there, and then I did take the gradient here. So I use 0.9 divided by 1.7. Okay, and that gives me 0.529. So that gives you 0.352, 0.53 in grams per minute minus 1. So that's how I done that. Right. Chloroethanoic acid, stronger acid than ethanoic acid, 1.3. Sketch in the figure 2 a curve that would expect when 25 centimeters of 2.23 mole cube solution of chloroethanoic acid reacts with excess sodium hydrogen carbonate. Because it's a stronger acid, it'll be a steeper curve. So you get a steeper curve, and then it flattens up at the same place. That's how you do it, okay? So just why chloroethanoic acid is stronger acid than ethanoic acid, because chlorine is an electron withdrawing group, so we can the OH bond. Okay. Let's do question number 2. Question number 2: A and B react together in the presence of acid catalyst. You got A, 2B, C, and D. The rate equation of this reaction is rate K equals K B squared times H plus. So table 1 shows that how the values of relative initial rate varies with different concentration of each reactant at the same temperature. So it says complete the table by calculated missing values. So the first thing I did here, I used these values to calculate K. Okay, so then once I got K, I used K values to calculate relative initial rate, and then so I'll calculate that as 1 there, which is K is there, 250. Then the second one I did was 1 here, and then I calculated this one B. You have to look at here, which is B squared, gives you 0.669 divided 250 times 0.1. That's what I did there, and it gave me 0.0256. Okay, and then B gives me 0.16, which is you got root of that value that gives you 0.16. So you always use this equation, calculate the values needed here. Then I use those values there plus K constant to work out initial rate here. So I put it all in here. So if you can see, so that's 135 here, that's 1 here, and that's 0.16 here. So that's how I did it. I hope it makes sense. So a suggested mechanism for the reaction with those, you got the mechanism there. Deduce rate determining step for this reaction, give a reason for your answer. Rate determining step is step 2, okay? Because the slowest step, as the B and H plus are both step as B and H and both in the rate equation. So they're both in rate equation. So you look at the rate equation, whatever is your rate equation is in your slow step. Anything else is not, okay? So it has to stop here. So slow step here, or rate determining step is here.